Okay, again, chapter 3, part 1, exponential functions. Talked about parent functions back in chapter 1.5, and today we're going to talk about a new kind of parent function. Algebraic functions can be completely described by addition, subtraction, multiplication, and division. Transcendental functions cannot be completely described by those four operations. An exponential function is a function of the type y equals a times b to the x, where a is not 0, b is greater than 0, and also not equal to 1. Notice that the x, the variable, is in the exponent. And now we're talking about the natural base. So the natural base relates to the compound interest formula. Euler thought about what happens to the interest as I compound a loan more and more frequently. And the example I gave, I lend Colin $1 and he owes me $2 back the next day. So if I compound it twice, he'll owe me $2.25. It's all right. If I compound it 3 times, a bit more, 4 times, a bit more, and so on. But as I compound it, as the number of times I compound this interest approaches infinity, this approaches a constant value, which was not what Euler expected. He expected it to diverge to infinity. So you would think eventually Colin would owe me an infinite amount of money. Well, that's not the case. The most he could ever possibly owe me is about $2.72. So the limit as the compound interest situation approaches infinity here, and again, this is with $1 as your initial principal and 100% as your interest. So we're making it as simple as possible. So if I do this, it's going to be about 2.718, and we call that number E. So E is the limit as n approaches infinity of 1 plus 1 over n to the n power. And you'll see this number on your calculator. You may have seen it before and wondered what the heck it was. Well, here you go. It's an old guy's obsession about money from the 1700s. He was a wealthy man, so he lent out a lot of cash. Also famously debated Diderot in front of Catherine the Great. Diderot was an atheist and Euler was a religious person. So they debated. Catherine used that debate to decide whether to move Russia in a secular direction or a religious direction. Euler was considered to have won by Catherine the Great. Euler's special formula, which I discussed very briefly, it includes E times pi I plus 1 equals 0. So this is a bit of mathematical mysticism. Nobody's quite sure why these fit together so perfectly. Perhaps indication of a higher power, at very least a higher mathematics. But Euler presented this as evidence of God's hand in the universe. And Catherine was swayed. Okay, so one more definition here. Actually, yeah. So the natural base is E. And remember, we described what that was in terms of a limit, and it's about 2.718. Continuous compound interest, so that's A equals P times E to the RT power. So that's a formula for infinitely compounded interest, which is not a situation you see in banking. It is a situation you see in nature. So a modified version of this formula describes the growth of bacteria, for example. Because bacteria do not stop reproducing, no matter what. Kind of like the Kardashians. Okay, so here are some examples of an exponential function. Here are some non-examples. Well, what makes these non-examples? Notice, and let me expand the size here. Computer, enlarge. Do you see how the x is the base, not the exponent? So that's not an exponential. This has no value of x. It has pi in the exponent, which is weird, but it's still a constant. It's not a variable. And this is 1 to the x power. So the x is in the exponent, but again, 1 to any power is 1. So this would decay to a constant value. And then over here you have some examples of exponential functions. So let's sketch and analyze the graph of the following. Y equals 4 to the x power. And I want some characteristics described here. Domain, range, intercepts, asymptotes in behavior, and intervals of behavior. First of all, this is going to grow and approach the x-axis very rapidly. So exponentials, the rate of change is variable, of course. It goes up faster the further you get from the origin. So it's going to not require a lot of x values to really get to some high y values typically. And a lot of that depends on the b value, but in general, you should expect that to be the case. So if I were to consider some points here, so -2, -1, 0, 1, 2. -2, that's 4 to the -2 power, which is also 1 over 16. And 4 to the -1 power is 1 over 4. 4 to the 0 power. Anything to the 0 power is 1. And then 4 to the first power is 4. 4 squared is 16. So I've got 1 over 16, which is just barely above the x-axis. 1/4, still a little bit. 0, anything to the 0 power is 1. Anything to the first power is itself. And then 4 squared is 16. So we see this distinctive exponential growth. Exponential growth is scary because it's unsustainable in nature. So the human population on this planet, for example, is growing exponentially in a way that's not sustainable. The current growth rate is obviously not going to work long term. The growth rate in most first world countries is actually negative, America included. So we have less children than our population. We don't replace every member of our population that dies, in other words. But we do have positive growth through the mechanism of immigration. Okay, so here's a sketch of the graph. First of all, the domain. What x can I plug in here? Well, any of them. X is a real number. Any x value will work. The range, however, is constrained. It's going to be y greater than 0 because I could never quite get to the x-axis here. Asymptotic behavior. Asymptotes. And that's going to be a horizontal. Horizontal asymptote at y equals 0. End behavior. So that's the limit as x goes to infinity of f of x. And that's going to be positive infinity. And the limit as x goes to negative infinity of f of x. And that's going to be 0. So it goes to infinity to the right and then 0 to the left. And intervals of behavior, there is only one interval, and that is from negative infinity to infinity, on which it is always increasing. So those are some characteristics of that relationship. And you'll find them to be generally true. when the base value is greater than 1. So all those characteristics I described are true for every exponential function where the base of b value is greater than 1. The sketch of the graph would clearly be just a touch different, steeper or less steep.
So what does it say with the asymptote thing? What does that say?
Horizontal asymptote at y equals 0. Remember, I shall ever henceforth abbreviate horizontal asymptote as HA because it takes about 30 seconds to write that. And if I write it 500 times over the course of the semester, that would be a waste of about 250 minutes. About 4 full classes writing the word horizontal and asymptote. Just show up when you feel like it.
Yeah.
It's all right. Dang, they gave you the whole visitor pass and all that.
That's the new tardy walk-in thing.
Man, they're hardcore down there nowadays. Well, let's see. Tardy bonk. So we're talking about exponentials. Good question, Rachel. Other questions? All right. In that case, let's go on to a second example. So here we have a negative x, and I want you to make note. So y. I could also describe that as 1/5 to the x, and let me prove that to you. And I'll make this second graph a fat line so we can see where it overlaps and so forth. Well, it's pretty crappy zoom. Let me try that again. All right, so if you see a negative exponent, that can also be described as a fractional base. So when we have a fractional base like this, it will have a similar predictable set of values. So if I start making some x's and y's here, this is 1/5 or 5 to the -2. And so that's 5 squared or 25. And 5 to the -1 is 5 to the first power, 5. 5 to the -0 is 5 to the 0, which is 1. Anything to the 0 power is 1. 5 to the -1 is 1/5. 5 to the -2, 1/25. So again, characteristic behaviors. So let's sketch the graph based on those points. So at -2, we've got 25, so that'll be way up here off the graph a little bit. -1 is at 5. 0 is at 1. 1's at 1/5, and 2 at 1/25. So you see how this is sort of the inversion of the previous graph? It's actually rotated around the y-axis. So once again, the domain is going to be x is a real number. The range is going to be y greater than 0. The asymptote is going to be a horizontal one at y equals 0. Intercepts, I didn't talk about that last time, but so it only has a y-intercept at y equals 1, and that would be the same for the previous one as well. End behavior, so that's the limit as x goes to infinity of f of x, which in this case is 0, and the limit as x goes to negative infinity of f of x, which in this case is positive infinity. Those are reversed from the previous. And the intervals of behavior, once again, there is only one interval from negative infinity to infinity, and it is decreasing throughout. So that's an analysis of when we have either a negative x and a base value greater than 1 or a fractional base. Stop me if you have a question, a thought, or comment. Apparently the vaccines had a huge setback yesterday. Some large number of the participants had a reaction. So they're dropping back to punt, I guess. Extends the expected timeline for the vaccine pretty considerably. So the corona situation drags on. Okay, so I don't think we need to do another one of those. So there are basically two types. There's exponential growth, like the first one we analyzed, 4 to the x power. And there's exponential decay, which is like the second one we analyzed, 1/5 to the x power. So if the base value is greater than 1, you get exponential growth. If the base value is between 0 or 1, then you're going to get exponential decay. So things that decay exponentially, car values. That's why buying a new car is a stupid investment. Literally the dumbest thing you can do financially. Maybe you have enough disposable income where it's not a big deal to you. And in that case, okay, feel free to throw your money away. But know that's what you're doing, because a new car's value depreciates exponentially. In other words, it loses a lot of value very quickly. So you drive a new value off the lot, you lose a chunk, or a new car off the lot, you lose a chunk of value, first of all, because it's no longer a new car. And then the value itself decays at about 8% per year. So if you paid, I don't know, 40 grand for a Dodge Charger, in about 5 years, it'll be worth 15,000. Not a good investment. In fact, the worst sort of investment. Boats, similarly. But real estate, houses, well, there you have exponential growth. So real estate is a very sound investment indeed. But cars, boats, not. So people that have invested a lot of wealth in things that decay exponentially, not good managers of their money. Okay, so f of x equals 1/2 to the x. Let's describe that. So once again, we use these points. So 1/2 to the -2. That's 2 squared, or 4. Remember when I take in a trick, an algebraic trick I'm using here, is 1 over, well, I'll just do a over b. A over b to the -n is b over a to the positive n. So if you invert the fraction, you can change the sign on the exponent. So 1 over 2 becomes 2 over 1. And then 1/2 to the -1 is 2 to the first power, or 2. 1/2 to the 0 power is 1. Anything to the 0 power is 1. Anything to the first power is itself, and 1/2 squared is 1/4. So there's some points for us. You should be able to reproduce this table. If you can't, go back and Study some of your rules of exponents and so on. So let's see. So -2 goes to +4. -1 goes to 2, 0 to 1, 1 to a half, 2 to a fourth. Notice the graph is a little flatter here than last time because 2 is less than 5. So the bigger this denominator is, the steeper it would be here. And conversely, if we had a base greater than 1, the bigger that value was, the steeper it would be on the other side. Okay, so first of all, the domain, x is a real number. The range is going to be y greater than 0. And then they wanted intercepts. So that's going to be a y-intercept at y equals 1. The asymptotes are going to be a horizontal asymptote at y equals 0. So it shares a lot of these characteristics. And let's see, what else was it? In behavior, intervals of behavior. So in behavior, the limit as x goes to infinity of f of x is 0, and the limit as x goes to negative infinity of f of x is positive infinity. And then one interval, and it's going to be from negative infinity to infinity, and it is decreasing throughout. Stop me if any of that confused you. Notice that's identical to the last one we did. You should be able to graph and analyze exponentials at this point. You can't, you haven't been paying attention. Shame on you. Einstein once famously said, the best a teacher could ever do is give a student the opportunity to learn. I'll always give you the opportunity. I can't. All right. So let's do some transformations. So we're going to talk about 1/2 to the x power, which is what we just sketched. And we're going to think about what happens if we make it 1/2 to the negative x power. So the graph that we just drew, you'll remember it was something like this. So that's going to be 1/2 to the x power. But I want to graph one half to the negative x power. So I need to remember what sort of transformation takes place when I multiply the input value by a negative. You remember that reflects us over the y. So if I multiply the output by a negative, it reflects us over the x. If I multiply the input by a negative, it reflects the graph over the y. So in other words, something like that. And we'll graph them both on our calculator to confirm our prediction. So I'll graph 1/2 to the x power, and then 1/2 to the negative x. There's the first one, the red line, and then there's the green line. So the primary difference between this graph and mine is it approaches the x-axis a little faster, but it's hard to do that precisely by hand. Questions about this? Anybody? All right, cool. Chapter 3, I think, is a little more interesting than 1 and 2. It's less overlap with Algebra 2. Okay. So here we got 1/2 x and -2 negative 2 times 1/2 to the x. So we're going to have two transformations that take place. First of all, the output multiplied by a negative, that's going to flip us over the x axis this time. And then that 2 is going to be a vertical stretch. So once again, starting with that original graph, you remember it was something like this. So that's our f of x. So we're going to flip over the x-axis and be a little steeper. So something like that. And let's see how that, how accurate we were by punching it in the calculator. So first graph, second graph. Yeah, the difference in steepness is subtle, but it's there. Because exponentials are so steep to begin with. It'd be sort of like if you yelled in a room that was quiet, like a library, versus yelling in a room where 10 people are already yelling. It's going to be more difficult to discern your voice in the second scenario, and more difficult to see the steepness when the function's already pretty dang steep. Questions about this one? Transformations, that's what we're doing. Transforming graphs. All right. Use the graph of y equals 3 to the x power to describe y equals 3 to the x minus 1 power. So you try this one on your own. Sketch it first, then use your calculator to confirm your sketch. Minus 1 is in the exponent. Let me write that in a way that's more obvious. So sketch the graph of 3 to the x, and sketch the graph of 3 to the x minus 1. Tell me what the differences are. Let me know if you get stuck or confused. All right.
I got the price for it. I'll take the X.
Well, remember when I subtract 1 from the input, that's going to be a horizontal translation. In other words, it's going to move it a certain direction.
So just gonna-
Think about where minus 1 would move it. And remember that input vectors behave often the opposite way. It's going to actually move it 1 unit. Yeah, there you go. Yeah, once you have sketched your prediction, use the calculator to confirm or refute your prediction. Or a computer is fine. But I do encourage you, once again, to get a PI because ACT is the primary reason. So much of what I do is valuable for the ACT. In fact, we cover every possible question. And scores at some point.
Can I borrow a calculator?
Sure. Let's see. Where did I put those? Oh, here we go. Don't forget to give it back to me, gentlemen.
No, we're just
good question. Rachel said, when I sketch it, how can I make my sketch a little more accurate? Well, we know it's going to have a few characteristics. First of all, because it's exponential growth, it's going to approach the x-axis here, and it's going to diverge to infinity here. So I know that. I also know it's going to go through the point 0, 1, because every exponential function goes through the point 0, 1. Furthermore, I know it's going to go through the point 1, B. So 1 is going to go to 3. So with those 2 points, I can make a pretty dang accurate sketch. If I move those points over one place, I can make a pretty dang accurate sketch of this one, because this is going to move, of course, 1 unit right. All right, questions about this? All right, good. So y equals e to the x and y equals e to the 3x. So we're going to compare these two. First of all, e, remember that's just a constant value. It's an important constant, but a constant nonetheless. It's about 2.718. So I know, as we just discussed, that that's going to go through the point 0, 1 and 1e. So just less than 3. And then around that, it's going to behave in this characteristic exponential growth way. So that's easy enough. And then this 3. Remember when we multiply the input by a value greater than 1, and input effectors behave the opposite of the way you might predict. It's going to be a horizontal compression. So it's going to compress it towards the y-axis. So the new graph will be something like that. Let's test our prediction here. And make note of this, because this is probably the first time you've ever seen me use E. It is on your calculator. It's down here, you see natural log, LN, the third button up from the bottom on the left, bottom left. If it's in yellow text, you have e to the x. So if I hit second and natural log, it gives me e to the, I need to put that up here too. So e to the x and then e to the 3x. And we'll make 3x a fat line so it's more easy to distinguish, because this difference will be subtle. So here's e to the x, and here's e to the 3x. Boom. Yeah, boys. Questions about this? Anybody? Okay, cool. Okay, e to the negative x minus 1. That'll be an interesting one. This one's going to be kind of tricky, because when I have a negative multiplied by the input and also a constant value modifying the input, it's going to probably be easier for you to analyze if I go ahead and factor out that negative. So, and we can look at the graph here and see, and I'll kind of zoom in. So I'll do negative x minus 1. So this right here would make you think it's going to move to the right, but let's watch and see what actually happens. And let me change the window. We don't need all that x. So the negative is going to shift us left in this case. And I know that's kind of hard to tell. Let me get rid of the, yeah, well, there's no easy way to do that because it's also flipping us over the y-axis. It makes it a little confusing, but so we're flipped over the y-axis and then shift a unit to the left. You see how that would have been hard to determine looking at just this negative x minus 1. So factoring out that negative value is going to help you analyze this, because what's actually going on here is we're flipping over the y, and then we're going 1 unit to the left. And we see both of those things here. We give it just a little more x values. Maybe it'll be more obvious here. So we're flipped over and shifted left a little bit. But again, be careful when you have both a negative multiplied by your input and then a constant modifying your input. Best to factor out the negative in that case. All right. 2 times e to the x, that's boring. That's just going to be a vertical stretch. We've seen a lot of those already. Okay. So here's one for you guys. See if you can sketch that graph. Predict those transformations. Don't use your calculator until you've attempted to sketch it by hand first. And then use your calculator to gauge the accuracy of your sketch. Let me know if you get stuck. Excellent, sir. Oh, it's excellent. All right, so let's talk about the sort of transformations that are taking place here. Bristol, what this negative going to do?
Flip it over the x.
Very good. So we're going to flip over the x. Jesse, what about this 3?
It's gonna compress it.
Well, you could describe it as a horizontal compression, but more accurate would be a vertical stretch. probably noticed that a horizontal compression and a vertical stretch are basically the same thing. So always use this term as well to be more completely accurate. And then Ian, what about this plus 2? What's that going to do to us?
Move it to the left.
Good. 2 units translated left. Okay, so we're starting here, flipping over the x, stretching it out, and moving it 2 units to the left, something like that. So let's graph it and see. There we go. Questions about that?
I didn't get anything. Something else.
In your calculator?
Oh, yeah, I did put the.
That would do it. That's so easy to hit the wrong button on the calculator. You've probably seen me do it a million times by now. Well, also because this interface is wonky, but in real life too, it's easy to leave off a negative, leave off a parentheses. It's going to happen to you. And it's going to happen on the ACT because you guys familiar with Murphy's Law. What can go wrong will go wrong. If you use that to guide your decisions in life, you'll never be disappointed, only happily surprised when something actually does go your way. There are some mechanisms in the universe that make an unhappy outcome a little more likely. Second law of thermodynamics, etc. So Murphy's Law is a good principle to use when planning for the future. The compound interest formula, A equals P times 1 plus R over N to the NT. Make that a little larger. And let me tell you what these parameters mean. So first of all, A, that's the amount at time T. P value is the principal. 1 is a constant. R is the rate as a decimal. As a decimal, very important because a lot of folks will get these problems wrong because if it's 5%, they'll plug in 5 here, not 0.05. So the rate must always be converted to a decimal if it's initially in a percent form. Then the N value is the number of times compounded. Number of times compounded per T. And then T is, of course, time. So R, rate is a decimal. P, principal. A is the amount at time T. And the number of times compounded per T. Most banks do quarterly, so that would be 4 times per year. And the interest rate most banks offer you is abysmal nowadays. Significantly less than 1%. I think I might get 0.25% or something for my savings account. That's why real estate's a much better choice, because it grows exponentially. If you ever find yourself in possession of a lot of capital, don't just leave it sitting in the bank, because that's not going to be a good way to grow your money. You should invest in something that has a historically exponential growth rate. Around here, real estate's a pretty sure bet, but it's not always. In big cities, for example, Seattle has a super hot real estate market historically, but in the last 2 years, the inventory, in other words, the number of homes available for sale, has went up by 16,000%. So in other words, for every 1 home that was for sale a few years ago, there are now 160 homes for sale. So why the mass exodus from Seattle? I can only imagine the protests and unhappy political climate have an effect. Also, the place is burning. So I don't know if you saw the things online, but it looks like hell. Yeah, the West Coast is beautiful, but subject to a lot of natural disaster. Earthquakes, wildfires, mudslides, torrential rains. It's a crazy place to live. Beautiful when it's not in the midst of one of those natural disasters, but they occur far too frequently for my taste. Give me the good old mountains of East Tennessee. All right. So we're going to use the formula we just discussed. Mrs. Salisman invested $2,000 into an educational account for her daughter when the daughter was an infant. The account has a 5% interest rate. If Mrs. Salisman does not make any other deposits or withdrawals, what will the account balance be after 18 years if the interest is compounded quarterly? So in other words, the A value, when the P value is 2,000, and the rate is 5%, 0.05, people. Compounded quarterly means N equals 4, and T is going to be 18, because we're leaving it in there for 18 years. We'll use our calculator to estimate this value. It was an interesting characteristic of previous generations that they often grossly overestimated how money would grow in the bank. So they would speak with reverent awe of so-and-so whose parents put $1 in the bank when they were just a little baby. And now it's this, massive fortune. Let's dispel that nonsense, shall we? This is not quite right. Let me fix this. I need to put a parentheses on that last bit. Once again. So it's going to become about $4,891.84. 4891.84. So here the mother put in 2,000, and the result is a little under 5,000. Is this going to put her daughter through a nice college?
No.
Is it going to pay for her lunch for her freshman semester?
No.
Maybe. I mean, 5,000 is nothing to sneeze at. But in today's world, it's not going to get you to college. Now, if you avail yourself of every scholarship opportunity, that money could probably go a pretty long way. And you get the first 2 years of college free in Tennessee, which is really an awesome thing. Former governor put that in place, and it was really a cool mechanism for every student. Crazy if you don't take advantage of it. Because if you do 2 years at Northeast State, get your associates, and then you transfer to somewhere like, ETSU, and you do your final 2 years at ETSU, your diploma says ETSU. It does not say ETSU by way of Northeast. So the diploma is no different, and it's equally valuable. You paid half as much for it. Crazy if you don't take advantage of that. There are certain reasons why you'd want to go to a 4-year college all 4 years, but it would have to be the case for me that it's worth that additional cost. All right, same scenario, but this time she's compounded monthly. So we want to know A, when P is 2,000, and the rate is still 5%, but we're compounded monthly this time. So that'd be 12 times per year. What kind of effect will that have on this result? So if you don't already know, you can hit second and enter to re-input whatever you just put into the calculator. And that can save you some time in a situation like this. Yeah, I need to have 12 as the denominator here. There we go. So 4910.02 to the nearest hundredth. It's not exactly the way banks do it. They actually always round down, and that fraction of a cent goes to the house.
Mm.
So, but we'll assume they're fair, which is pretty bad assumption in the case of bankers. So before it was 4891, now it's 4910. So is that a massive change in the amount of money?
Not really.
It's very subtle. And you'll notice that we'll approach E. Remember the graph I showed you? We approach E pretty quickly. So the number of times compounded makes less and less of a difference as we increase those values. Still talking about Miss Salisbury, but this time compounded daily.
Dang.
Oh,
Holy molasses.
365.
So 2,000 times 1 plus 0.05 over 365. If we want to be super precise, we'd say 365.25. Why the 0.25?
That's leaf year.
Very good. But we won't worry about that word. They didn't have leap year as a mechanism in ancient times, and so the dates were constantly shifting over the centuries with the seasons. Only in, I think that the early Enlightenment was that fixed, if I remember right. All right, second, enter. I'm going to change this 12 to 365. And I change this 12 to 365. And then I hit enter. 4918.90. We're still changing just $6 or $8, man. That's nothing. Over the course of 18 years, this money's sitting in the bank, burning a hole in your pocket. You know, a lot of people develop a nest egg, and then some minor tragedy occurs. Car fails to function. You run over a nail, you got to buy new tires. I don't know. There's always some reason to spend that money. So it's very difficult to maintain savings as an adult. Okay, now the last one of these says compounded continuously. So this is the compound interest formula. And the real difference here, A equals P times E to the RT. Let me make this much bigger. A equals P times E to the RT. A is still the amount at time T. P is still the principal. And then E is Euler's number. It's about 2.718. And then R rate as a decimal. T is still going to be your independent variable, your time variable, typically. Pert used to be a popular shampoo in the 80s. I think it's actually still available somewhere.
I think it is. I was in 8th grade. That was good. Mistakes. I recommended that, like it's shampoo. So I think it's so great.
Yeah, as far as I know, it was a pretty high-end healthcare product in the 80s. In other words, it's something you'd find in, boutiques or fashion stores. And it has migrated its way downward, and now it's kind of a great value type brand. Interesting how that works. The same mechanism is true for names. If you read Outliers by Gladwell, he talks about names and the consequences of a name for the future of a child. For example, Candy, a name Candy makes your child more likely to be a stripper. But very rich and wealthy people have a certain group of names they're more likely to select for their child. And the next generation, those names migrate to the middle class. And the rich have a new set of names they use. And then the generation after that, those names migrate to the lower class. Pretty interesting mechanism. Okay, anyway, A equals PERT, continuous compound interest. So here we are, Mrs. Salisman. Man, we're still on Mrs. Salisman. This time we're going to do continuous. So we're going to use A equals PERT. It's 2,000 times e to the 0.05 times 18. This is going to be continuously compounded interest. We're compounding it infinitely this time. And it's going to be about 4919.21. So, again, back in when I was a kid, people would talk with reverential awe about so-and-so whose grandpa put $1 in the bank when they were a baby. And now here they are, a grown person with a fortune. Would that have really manifested into a fortune? No, you'd have like $3. So the generation before that, so my grandmother's generation, what they call the silent generation, the people that grew up during the Great Depression, had the opposite opinion on banks. They were very untrusting of banks. I wonder why. Well, because the banks failed during the 1930s and all their savings dissolved. So they used things like mattresses, cash under the mattress and so on. All right, so exponential growth and decay formulas. So these are the modified versions of the formula we discussed, A equals PERT, but in this case, it's often used to describe physical phenomenon, bacteriological growth, et cetera, et cetera. So this is just very much like what we saw. Exponential growth or decay, you just substitute N for A, N sub 0 for P, and you don't consider additional compoundings. So this is the formula for exponential growth or decay in the physical world. Just a rebranding of the variables. Let me make this much larger. That's ridiculously small. Can we get them both on there? Nope. There we go. So N equals N sub 0 times 1 plus R to the T, where N sub 0 is the initial amount of the bacteria, for example. And then continuous exponential growth. Here, you notice they use K instead of R. No difference, just a rebranding. It's like if I were to say the black cat or el gato negro. Means the same thing. The tall boy or el muchacho alto. The nice lady or el mujer simpática. La simpática. The generalization of everything in Spanish often confuses me. Who's not accustomed to that. Okay, moving on. Last example we'll discuss here. Stay with me, Jesse. So a state's population is declining. We just talked about this going on in Seattle, which is Washington State. Typically, most populations grow in most places. But there's inevitably an isolated location or two where the population decreases. Elizabethton's population decreased at a point early in my life when the North American radio closed. Young people had to move to find a job. But in this scenario, a state's population declines at 2.6% annually. The state currently has a population of approximately 11 million people. If this population continues to decline, predict the population of the state in both 15 and 30 years. So we're going to use that formula right here. Continuous exponential growth or decay. Well, it says annually though, so we probably should use this model. So yeah, we'll use the first model. N equals n sub 0 times 1 plus r to the t. So n equals 11. We'll just use 11 instead of 11 million. And 1 plus, and the rate is negative here. It's declining. Negative 0.026. And then we want to define this at both 15 and then at 30. So let's see here. So 11 times 1 plus a negative 0.026 to the 15. So that's about 7.4 million. And then to 30, it's about 5 million. So 7.4-ish million and about 5-ish million. So in 30 years, the population is more than halved. Okay,
Yeah, well, I'll do something wrong. My computer keeps messing up.
let's see what you got, buddy.
I'm not getting that.
Oh, this is the, you put a 0 in here? That should be a 1. Oops.
I was also getting rid of answers on the back section. Might get it here.
Do it to get those parentheses.
No.
Did you have the answer to that?
Yeah, but I didn't send that plate.
So this one's right, I believe. Be careful to put everything that belongs in the exponent. I think maybe might be the issue there, Jesse. Okay, so population decreases. Let's see. All right, so I think there's one exponential growth here, but you guys should be able to see how that would work. You just have a positive r instead of a negative r. We went a little longer than I had hoped anyway, so let me go ahead and give you the assignment for chapter 3, part 1. And that will be page 166, problems 12, 13, 21, 22, 25, and 31. And I'll freeze this. There we go.